right? So you imagine when the tow bar breaks, the van will of course keep going up, but the trailer going up with some inertia, and then it's going to stop somewhere and then slide back down, I guess. KE is like an input and GPE is like an output. So this is the work done against friction. It's like the cost you need to pay going up because there is friction. If you can move everything in the calculator, that's going to be fast. You don't need to simplify anything. This is a further math paper, guys, so you don't need to show a lot of working there, all right? Because you have a mass on top of B there. If you use a common sense, it should be about to tilt towards B, right? So get the sense of the friction right, because it can be either way, actually, depending on the case. Approaching a wall and separating from a wall, because the wall doesn't move at all, so you can use E to multiply this initial speed to get the final speed already. Let me check from the beginning. I see my mistake here. This is the mistake I have seen with many of my students, but oh no, that is 0. It's impossible. Okay, 7 minutes, 7 minutes. My time is running out. Oh no, I used the wrong value. So I lost -1, just 3 marks, I guess. 72 out of 75. Yes. Try to revise on how to prove the algebraic formula in projectile motion as well. This is the most recent year as of the time of recording, and it came up. Hi, it's me, Krubase. Today I'm going to do another walkthrough on an unseen paper. Now this time it is IAL M2, October 2024. Because mechanics papers are not exactly like pure math papers, so along the way, I'll try to give you some briefs about the concepts in mechanics as well. You can also use chapters in the description to jump to any other question. Otherwise, stick around. Are you ready? So I have hit the timer. Let's get started. Number 1. Okay. So at time t seconds, t greater than 0, a particle p is moving with velocity v. And here's v is a vector because there's component I and j. Position vectors are given relative to the fixed origin. At the time t equals 0, p is at the point with position vector that. Okay. So find the position vector of p when t equals 3. All right. So we are given the velocity vector, and the way to find the position vector is to integrate, guys. So if we integrate v dt, we're going to get s in terms of t. So s is the position vector. And now we are also given the something called an initial condition where t equals 0, where is the position vector, okay? So let's integrate v dt here. So this is acceleration. It's like a non-uniform acceleration motion because the two vectors don't have the same acceleration, so to speak. So if we integrate, we're going to integrate separately. So it's going to be integral 3t plus 2 squared dt for the I, right? And plus integral 5t t plus 2 dt for the j. And now because we want the position vector, right? So this is actually essentially, let's put that question 1. So this is actually position vector p, but I'll put it as s, right? Now, if you already use the bound here, so, okay, and put 0 here and t here and 0 here and t here, right? You can already change on the other side of the equation, which is this side, to be the actual position vector at times t equals 3 already. Oh, okay. Well, we're going to find time at t equals 3, so we got to get this later, but see if we need to use the position vector later on. No, actually, so I can already do this, right? So it's actually, so what do I do? Okay. Okay, so it's like this, guys. We have ds by dt equals v, right? So if we move dt to the other side, we get v dt. And if we integrate both sides, so this is already what you know. It's going to give you the position vector, but on the left side here is what I'm interested in, because if you put the right bounds at the beginning like this, so if you put if you put the initial location, let's say SI, okay, and we want the position vector as 3, so 3 second here, S3 is the thing we want, or I'll just put, yeah, S3 maybe. And this is starting at t equals 0 and then t equals 3 here. So you see, we can already put the bounds correspondingly, and this is going to give us the answer already, right? So, so let's do that. So we have S3 being what we want, right? So I'm going to put S3 here. So again, if you integrate ds, you're just going to get S, right? So this is just S, but then the initial condition and the final condition is going to be put there. So it's basically just S3 minus SI, and SI being the initial position vector, which is minus 30 and minus 45 there. So everything are separate into two components of vectors, right? So I'm just gonna, hang on. Let me just undo that, see if I can do that. Okay, yeah. So I'm just gonna put this into somewhere else. Okay. Maybe there. Okay. So if we want position vector as the third second, we can just rearrange this, but let's do the right-hand side first, all right? So integral of that, so we can do reverse chain rule there. So it's 3t plus 2 to the 3 over 3. Yeah. And I can also have, I should also change the bounds to 0 to 3, because we want from the initial position vector to the position vector at times equal 3 seconds. And then this is going to be I and j as well. So that's the I. And I'm going to put the bounds here. Yeah. So this is from 0 to 3. Okay. I already integrated that. Okay. And 3 cancel here, just to note. So this is for another one, the component j. We are integrating that. So it is probably easier to just expand it in. So expand it in, we get 5 outside. So I'm just going to put 5 here already. If you expand t in, you get t squared, and you integrate t squared, you get t cubed over 3, right? If you expand to t, if you expand t to 2, you get 2t, and if you integrate that, you get t squared, 2t squared over 2, so that's going to give you just t squared, all right? Okay, so that's the component j, all right? Okay, and with the bounds of also 0 to 3, yeah? So, I mean, as you can see, if you sort of solve, like put the limits in, the bounds in, the terms here, then you will get the value of the position vector here as well. So if I put 3 in, I get 5. So the top one would be 5 cubed minus, if I put 0 in, I get 2 cubed. Okay. For the bottom one, if I put 3 into the t cubed there, I get 9. And plus another 9 here, so that's 18, yeah? And if I put 0 in, I get 0, so that's nothing. So this is the substituted. Now, if we move this to plus the other side, so that's going to be plus minus 30 minus 45, right? That is going to be the position vector at time equals 3. So working that out, so this is 125 minus 8, so I get 117. 117 minus 30, I get 87, yeah? And then this is 18 times 5, so that's 90. 90 minus 45 is 45, yeah? So I think that is the answer, 87I plus 45J in meters, yeah? We can just put the units there. Okay, so let's check that again, actually. Yeah, 87. All right, so that's the answer for the first one. Okay, the second one, the part B, I mean, this is part A. Find the magnitude of the acceleration of p when t equals 3. Okay, so acceleration can be found by differentiating the velocity vector. Okay, so we're going to differentiate that. So it's going to be, if you move 2 down, you get 6 and then t plus 2. All right, just that, because we can use chain rule there. So this is I, and then you have the plus a j. So again, that is 5t squared. So if you sort of like ignore the 5, keep the 5 in front of everything, you have t squared. And when you differentiate t squared, you get 2t in the brackets. T putting into 2, you get 2t. You differentiating 2t, you just get 2. That's for the j. Okay, that's acceleration. And we want the magnitude, so we put at t equals 3. So acceleration would be 3 putting in there, so we get 30i plus 3 putting in here is 6 plus 2 is 8. 8 times 5 is 40. Okay, so that's meter per second squared. So the magnitude of acceleration, 3, 4, and 5, that's Pythagoras. So we get 50 meter per second squared. All right. Or we need to show some working there because it might be too fast there. Okay, just 30. Okay. And then question C, at time t seconds, p is moving in the direction of the vector 2i plus j. So moving in the direction of that is indicating that the velocity is not that vector, but only parallel with that vector. All right, you cannot equate it because moving in that direction only implies that it is parallel to that vector. All right, so we can equate the velocity vector to these guys. Okay, so the velocity vector, which is that, okay, and the j component. I prefer doing it in columns, guys, because it saves space. So if we expand the k inside each component, we get 2k here and only the k here for the y. So we have two equations, two unknowns. This is simultaneous equations, right? So we're going to have, for the first equation, see if we can do some tactics there. I think I'm going to, expand this. So I get 3. So expanding this complete square, t squared plus 2t plus 4. Oh, hang on. That's t squared plus 4t plus 4, sorry. And that's going to be put equal to 2k. The bottom one, after expanded, I'm going to multiply everything by 2 because I'm going to cancel k first, all right? So multiplying everything on the bottom by 2 while expanding in also. So I get 10t squared, yeah? And then plus 20t on the right, and then plus 2k here on the right. Okay, so 210, yeah, I'm happy with that. So if you subtract both equations, k will go away. I get 3t squared here subtracted by 10, I get minus 7t squared. 3 times 12t, 12t minus 20, so I get minus 8t. And 12t minus nothing, so I get plus 12, all right? And that is 0 on that side. So this is 7t squared plus 8t minus 12 equals 0. Now, I'm going to try factorize it first. Or I don't think so. Maybe, yeah, I'll try that. Because my calculator is not capable of quadratic solving. So let's try 2 and 6. That works, right? Okay, so this is going to be plus, this is going to be minus. Just adding one more page. So that means, let me check that if I expand. Okay, yeah. So t can only be a positive value, right? So we're not going to take that. That means the value of t here in seconds would be 706. Yeah, that's it. Because we want t, we didn't want k, and that's it. So we need to solve, don't need to solve for k. Question 2 already. Question 2, a particle q of mass 3 kilograms is moving in a smooth horizontal surface. Particle q is moving with velocity, that vector again, when it receives a horizontal impulse of that. All right, okay. Immediately after receiving the impulse, the velocity changed to that. So guys, in physics, impulse is equal to change in momentum. Okay, not only true in mechanics paper here, but in physics in general, you can also use this. So an impulse itself, momentum is mass times velocity. Okay, and P and V here are vectors. So if you do delta P, that would be M and then the final velocity minus the initial velocity in vectors. So I is a vector here, impulse, V and U are also vectors, right? But the magnitude of impulse is given to be that, so we need to plug in here. Okay. So, right. Okay, so if we plug everything in, mass is 3, and the immediately after receiving the impulse, so that is the velocity vector here. So this is x, y, right? That's the velocity vector v. And then I have a minus, right? So I'm going to do another brackets there. U is moving with velocity 5i. So I'm just going to put 5 there and 0 here because it doesn't say any j component. All right. Okay. So if we simplify this, we get 3x minus 5 and y for the impulse vectors, impulse vector. And we also know that the magnitude of this vector is 3 root 82. So we can do that. So that's going to be Pythagoras again. Okay, finding the magnitude of a vector is like Pythagoras. And we are given that this is 3 root 82, right? Okay, so that's 3 root 82. So yeah, we square both sides, right? So we're going to get something like a circle equation, but mathematically speaking. Let's carry on, right? The kinetic energy gained by Q as a result of the receiving the impulse is 138 joules. Okay, so kinetic energy gain, let's do delta KE here, is going to be the kinetic energy of the final velocity or final state after the impact minus the kinetic energy before the impact. So I'm using V and U here respectively. And just to simplify that, we can do 1/2 m and in brackets V squared minus U squared. And note that these V and U are the magnitude of velocity, right? And we're going to equate this to 138, yeah? So undoing the 1/2 there, I get 276 here, and then m is 3. So v squared, what is v? V is x and y, right? So if we do the square there, this is the square, this is the magnitude square. So it's just like doing Pythagoras again. So because v has x and y in I and j, so if you want to find the magnitude, you got to do x squared plus y squared square root. But this is the magnitude squared, so that would just be x squared plus y squared. And these are not vectors, guys. Don't forget. And similarly with the u, but the u, we already know that the velocity is in one direction. So the speed squared would be 25 here. So I'm going to minus 25 there already. So this is another equation, right? So we can plug it in there and solve for one of them. Let's see what we want. We want the velocity of q immediately after. So we want to find x and y basically. All right. Okay, so let's see if I can multiply. Sorry, I can divide. Okay, I can cancel this by 3. So I get 3, 8, 24, and no, 3, 3, 9, 2. Yeah, 9, 2. Okay. So, and then plus 25 on both sides. I get 1, 1. I'm just going to use calculator there just to be safe, guys. 117. So I have x squared plus y squared equals 117. Okay, that's the other equation. And if you bring this equation down, okay, so you have 3x minus 5 squared plus y squared. I'm squaring both sides, so that square root goes away. This one will be 3 times 80, no, 3 squared, which is 9 times 82. Okay, so that's 738. Okay, so what are we going to do with these? I think we're going to subtract them maybe. Okay, so this is number 2, this is number 1. I'm going to do 2 minus 1. Yeah. So I'm going to get 3x minus 5 squared minus x squared because I'm doing 2 minus 1. So the bottom one subtracted by the top one. And then I would have 738 minus 117. So I get 621 here. Yeah. Now, why am I doing this? Well, because maybe it's easier. Okay, expanding these out. 9x squared, and this is 30x, right? Expanding this complete square, basically. Plus 25 minus x squared equals 621. Okay, so this is 8x squared minus 30x. And 621, if I subtract that by 25, so I get minus 596 moving on the other side to subtract 25. I think I can simplify that a bit. So dividing everything by 2, right? So I get 4x squared minus 15x. And then this will be 298 equals 0. Yeah, that's right. Okay. Factorize. Okay, why not? See if I'm any luck with that. So 298 divided by 4. No, 4. That's not divisible. So 298 divided by 2. Oh, okay. So that's 149. Is 149 a prime number? Okay, okay. I think I'm gonna use the quadratic formula, guys. Probably safer here. So x equals minus b, which is 15, plus or minus square root b squared minus 4ac, all divided by 2a. Okay, so fraction 15. Let's do a plus first. 15 squared. So that altogether will be a plus 4 times 4 times 298 divided by 8. That is a horrible number, but all right. This doesn't give me any sense of getting it right at all, but it doesn't say exact. So yeah, this is a bit horrible. Okay, let's note the answer first, but if I put that to a minus, that's going to be a minus. So, ooh, okay, it is. Is it possible to get minus? Oh, x and y are positive constants. So it's not. So let's do a plus. So I'm going to note down the answer here first. Okay. And yeah, let's do 0, 7, 6, blah, blah, blah. And then I wonder if I can do exact, right? So I'm just going to do that. Okay. That doesn't seem like an exact number to me. Okay, okay. So let me check. Let me check from the beginning. Ah, I see my mistake here. This is a 15. Quickly here. This is a 15. Sorry, guys. I didn't see that. This is bad now. Okay. Okay. So this is a 15 and oh, this is also a 3y. Yeah. This is the mistake I have seen with many of my students, but there you go. I made it. Okay. And this is also a 9y squared if you square that, right? Okay, okay. I think this is fine because yeah, 1/2 m, undo the half, and then undo the 3. I get that. Yeah, it's just these. That is not fine. That is changed to 9y squared. And this side is still the same. All right. Seems like I need to change everything. Okay. Yeah, you know what? I'm gonna maybe do the algebra again here. That's bad. Okay. So Okay, so I'm just gonna make isolate y here. So this is y squared equals 117 minus x squared and put it in the y squared there. With expanding this, I get 9x squared minus 30 and 90x, okay, plus 225, expanding that. And then while substituting y squared with 117 minus x squared equals 738. Yeah? All right, but this time I think it's better because we can cancel the x squared there, if you can see that. So 9 times 117, I get 1053, and this is a minus 9 squared, guys. So we can cancel that. So this is faster. So 90x moving to the right, and on the left I have that plus 225 minus 738. Ah, nice. That feels much better. So x equals 6 actually. All right. That means y would have to be what? So y is 117 minus 6 squared, square root with being a positive constant. Okay. So that would be equal to square root of 117 minus 6 squared. That is just 9. Okay. So velocity vector of q is 6i plus 9j meter per second. Okay. That's it. Number 3. Number 3 seems to be about energy and power, I guess. So the van of mass 900 kilograms is moving up straight road, inclined at an angle alpha, blah, blah, blah. So I'm just going to read the first part here. A, find the acceleration of the van at the instant when the speed of the van is 12. So guys, the main equation we use in power and everything here, climbing up a ramp usually is power is equal to F times the force. Sorry, F times the speed. Okay, because yeah, see if it's constant. Yeah, we have the resistance, blah blah blah. The tow bar is modeled as a light rod. The engine of the van is working at a constant rate, so that's important. Power is constant. Okay, at 15 kilowatts. Okay, yeah. So because P equals FV, so the F, the engine force, yeah, would be equals to power divided by speed. Okay. So moving up the ramp here, okay, alpha there, we would have acceleration of the van at the instant when the speed is 12. Okay, so the van here, the van is the thing that is towing a trailer. So trailer is the one behind it. So this is the van moving up with the engine force. But don't forget, guys, if you are towing something up, that's going to be something called a tension, right? So there's a tension here pulling it down, where also you also have mg. Yeah. So let me draw a separate diagram for the van and the trailer. There's a tension from the tow bar and the weight component downwards. Let's see if there's any. So this is the mass of the van is 900. So this is 900 g sine alpha. That's usually the weight component. So the weight component on a slope like this is usually mg sine alpha. You can just do the geometry there, but it is usually that. We can take it as that. So, okay, yeah. Resistance of the motion on the van from the non-gravitational force. Yeah, so there's another resistance here we need to take into account. So there's another force here, friction, 400. So let's do sigma F equals ma, Newton's second law. Okay. So because we are going up as an acceleration is upwards there, so we're going to do the engine force, which is power over the speed, right? Minus the tension, minus 900 g sine alpha, minus the non-gravitational resistance equals mass 900 times acceleration. Seems like we are stuck with many parameters, but we're gonna do simultaneous, right? And it doesn't tell, oh, okay, this is already telling you that speed is 12. So before substituting everything in, we're just gonna do simultaneous first. So this is for the van and for the trailer. Okay, so the trailer is going up by what? So let me draw a trailer here by a tow bar, of course. And then there's a friction. And then there's a weight component as well, which is 200 G sine alpha, right? And that's it. So for the trailer, T is the driving force forward, upwards, minus the resistance, 240, minus the weight component, 200 G sine alpha. And I think that's it for the trailer. Equals, what's the mass? 200. And acceleration is the same because this is a connected particle system, all right? If you add up the two equation, yeah, T will cancel, and that will leave you with this term, P over V. Now we're going to plug in now, 15,000, which is the P there. V is 12, so I'm just going to put 12 in here. T goes away, okay? And considering the weight component first, so 900 G, okay? So I'm going to do like this. I'm going to do minus in front because this is, we adding them up. So there's a minus 900 and a minus 200. So I'm doing minus 900 plus 200 G sine alpha all together like that, right? So, and that's going to be 100, 1,100 G sine alpha. Sine alpha should be 1 over 25, just simplifying it a little more. Now, both of the resistive forces would add up to minus 640, yeah? And the masses here would add up to 1100 A, right? So that's it. Now, if you solve for A, you will get the thing. And does it want in any? Yeah, we can do two significant figures. So I'm just going to put everything in my calculator here all at once because mental math seems a little mind-blogging here. Okay. And the G value in this paper is 9.8 usually. Okay, so we're going to take 9.8 there because it doesn't want in terms of G, so I don't need to do a G there. Okay, minus that, and then all divided by 1100. Okay, so just checking if I put everything in, all right. That should be fine. So that's 0.1625 dot dot dot, which is 0.16 meter per second squared. That's A done. That's A. And B, at the instant when the speed of the van is 14, the trailer is passing the point A on the slope and the tow bar brakes. Oh, poor guys. The trailer continues to move up slope until it comes to rest, right? So you imagine when the tow bar brakes, the van the van will of course keep going up, but the trailer is gonna keep going up with some inertia, and then it's gonna stop somewhere and then slide back down, I guess. All right. The resistance to motion of the trailer from non-gravitational forces is still modeled as a constant force of magnitude 240. That's talking about the trailer. Use the work energy principle to find distance AB. All right, so we have a RAM again. Now, okay. So this is the break point, maybe. The break point. It breaks at, okay, yeah. Point A is when the thing breaks. Okay, yeah. So this is when the van is already at 14 meter per second, and so is the trailer, right? Because they are connected. Okay. But of course, the trailer will not catch up the van because the van is going up with some power, so it's going to accelerate up still. But we don't care about it. We care about the trailer, right? So because we want to find the distance from A and then to some point here, B, imagine that the van already goes quite far up. So we're going to need to do some energy there, all right? So let's say that AB is distance D, yeah? So I'm just going to do D here. And because this is still the same angle here, alpha, right? Because this is alpha still, doesn't change the ramp. That means if we want to find the height change of this distance AB, it's going to be just doing the trigonometry there. So this is D sine alpha, right? Okay. So let's do some energy here. So from energy conservation of energy. So the loss, KE loss, and then KE loss equals GPE gain plus some work done against friction. All right, that's the general equation there. Because you need some energy from the KE loss to work against friction going up, right? So you put it on the right side. It's more like this, guys. If we have a Sankey diagram, KE is like an input and GPE is like an output, but you have some energy waste. That's a good analogy there. So this is a work done against friction. It's like the cost you need to pay going up because there is friction. So we don't actually like friction that much if we want to conserve energy, like, or increase efficiency here. But anyway, I'm just going to go ahead now. I'm talking too much. So KE loss, we want the point where it is stopping. So KE loss will be totally calculated by the 14 meter per second here, right? So that's going to be 1/2 m of the trailer is 200. Yeah, hang on. Let me just, so 200 v squared, which is 14, because that is also the speed of the trailer. And then equals GPE gain. So the trailer is GPE is MGH, so it's 200 G. And then H is D sine alpha, right? Because this is the height gain. Sine alpha is 1/25. Yeah. Friction is the same as 240, so that's 240 times D. So that's it. That's the equation. Very simple. You just solve for distance AB, which is the D there. Okay, so I'm just going to do the algebra there in my calculator. So if you can move everything in the calculator, that's going to be fast. You don't need to simplify anything. This is a further math paper, guys. So you don't need to show a lot of working there. All right. So imagine we are simplifying the D terms on the right side, adding them up and moving them to divide the left term. So I'm just going to do the left term right here. So that's 0.5 times 200 times 14 squared. That's the kinetic energy lost. And then if you add 200 times 9.8 times 1/25, okay, at 240. That's the work done against friction. It's just F times D, yeah? I forgot to mention that. So this is F times D, right? Yeah. So that's already the answer. So D is 61.6 meters, right? So that's it. 61.6 meters is the answer. I'm just going to go ahead and do question 4. All right. So this is probably about center of mass. Uniform lamina ABCD shown in figure 2 is in the shape of an isosceles trapezium. That means AB equals CD. BZ parallel to AD and angle BAD is equal to that. Yeah, of course, of course. BZ is 5A, blah, blah, blah. Perpendicular distance is 3A. The distance of the center of mass of ABCD from AD is D. All right. Okay. From AD. Okay, so we're gonna find from the bottom here. So that's the center of mass. There you go. Okay. So yeah, we're gonna show that the location of D is 17 over 12 away from that line. So, well, we can split it into two triangles like that. And we're going to do y, yeah, because x is already in the middle. So we're going to do y bar there. Yeah, so y is taken from the bottom part there. So we're going to split, right, into three shapes here. Okay, so we know that the center of masses of a triangle and the rectangle are, so this is 1/3 from the corner, from this corner here. So if you have a right angle triangle, so the center of mass here is going to be 1/3. So this is, let's say if this is a height, this is a base, it's going to be 1/3 the height on that side and also 1/3 the base on that side, and the other one would be 2/3. So depending on which side you take, but so again, center of mass will be the sum of mass times y divided by the sum of mass, right? If you only find a center of mass there. Okay, so there are three pieces here. And M in this case can be taken as area because we are dealing with uniform lamina. So here I'm going to do area instead and sum of area, right? Okay, so the triangle area is 1/2 times the base. The base on this side is, so that's 7a minus 5a. So you get 2a, and 2a divided by 2, you get just 1a. That's the base, and the height is 3a. That's the area. Then the area multiplied the y, which is 1/3, as we already discussed, 1/3 of 3a, right? So that's the y of the just one triangle. And we are adding them up by 2. So it means I'm adding 2 of them. So I'm going to do 2 here. And then I'm just adding with the rectangles. Okay, so the rectangle, the area is, that's going to be 5a times 3a. Just doing everything here first to get the working marks. And then what is this? This is, yeah, it's the center, right? So it's 3/2a, right? Shouldn't have asked for that. And then the total area is just, I can use trapezium formula, half times the sum of the parallel side, so that 12a, and then the height. Okay. Okay, so let's simplify there. I can simplify every 2a's there. Yeah. And then I can cancel the 2 and the 2 here. And then 1, 3 and 1, 3 here. So the first term on the top part is 3a plus, yeah. And then the second term is 9, 45, 45 over 2a. That's a bit horrible. And this is 6, 18 down here. Okay, so doing the fraction there, 2 multiplied 3, I get 6. 6 plus 45, I get 51a over 36, because 2 has to be brought down, and that is it. Except I can simplify by 3 a little more, I get 17 over 12a, yeah, because that can be divisible, divided by 3. So as required. Then now we have B. So what do we do with B? The uniform lamina, that is a rectangle with, okay, now we have a different. Okay, so it's like taking this shape as a cutout, basically. PS is parallel to AD now. Okay, so PS parallel to AD. Yeah, okay, okay. The perpendicular distance between blah, blah, blah. Ah, okay, so this is finding the center of, no, the angle. The template is really suspended from P. Okay, so you know what? I'm just gonna, what should I do? I'm gonna need that shape, because normally if this is a real paper, I can draw it in the shape. So let's bring it to this app right here. Okay. Okay, so I get the image now. hang freely from P in equilibrium with PS at angle theta from the downward vertical. Okay, so PS is gonna make some downward vertical. So I think, yeah, so the center of mass, imagine if you cut out everything, including this bit from the trapezium, you're gonna have still the center of mass exactly at the middle. And by the middle, I mean here. But because you have more mass on the top part, so the point they assumed center of mass when it's totally cut out like that would be moved up a little bit, right? Because you have more mass here towards the upper direction, yeah, higher up. So that means the center of mass here from this cutout has got to be somewhere there, and we hang from P, yeah. So let's draw a sensible center of mass like that, and this will be the vertical. So this is the downward vertical would be like this. Okay. Right. So we are finding this angle right here, theta. All right. Now, before we do that, we need to find a new center of mass. Yeah. So the new center of mass is gonna be around there. So let's do new y here again, y bar. So now this y bar will be equal to, well, again, guys, we can do subtraction method, where you have a bigger shape subtracted by a smaller shape, right? And again, but it's also sigma a y divided by sigma a. All right. But sigma in this case also includes subtraction if there is, right? So I'm going to do a bigger shape, which is the, okay, so I'm going to do this one minus this trapezium inside. So the bigger one has the area of 5a times, just going to write that down maybe. So 5a times 9a and times the center of mass of the bigger one without the cutout would be 5 over 2a, right? Yeah, just at the center there. And minus, right, the cutout. So the cutout again is the trapezium. So we can take the area down here, 1 over 2 times 12 times 3. So that is, I'm just going to write down. Right? And then this is going to have to multiply by the earlier location here, but this is measured from the bottom. You got to be careful, right? So 17 over 12a, but we need to add this bit as well. Okay, so that bit is what? We have 3a here. So that's another a there, another a here. So this is going to be a plus 17 over 12a, right? From the bottom of the big rectangle. That's the center of mass of the trapezium. And then divided by the subtracted area. So this is 45a minus, so this is 18, sorry, a squared, and this is 18a squared, right? Just the area of the trapezium there, right? Yeah. Okay. So just working out there, I think I can cut the a squared, the a, and a here. So I'm just going to be left with a. So on the left part on the top, I get, what is that? 25 times 9, that's 225 over 2, minus, this is again cut, I get 6. This is 18, so 18 expanding into the brackets, I get 18 a plus, okay, calculator, or hang on. So this is altogether in the brackets, I have 29 over 12, right? Yeah. So 18 times 29 over 12. 18 times 29 is 552. So this is going to be 552 over 12a. Yeah. And I can cancel that a bit. So that is going to be 276 divided by 6. And that's still divisible. Okay, hang on, there's another 2 there. So 3 here, and then 138. Yeah, I'm just simplifying it first. And all this divided by, that is 27, right? Okay, so we're gonna simplify the fraction there. So that's 225 times 3 minus 2 times 138. That is the top bit there, 399a divided by 6 times 27 down there, 162. So that's basically the location from the bottom. I'm just going to keep it as that first because we need to find theta. We don't want that anyway. Okay. Now, yeah. So we know that the x location will be in the middle. So that is 9 over 2a. So we can do this triangle here, right? This is 399a over 162. And this is 9 over 2a, right? Okay, so yeah, that's going to be theta there because it has to pass the center of mass. So theta here is going to be equal to arctan of that, because we need to use a calculator anyway. So arctan in degrees, right? Yeah, in degrees. So arctan fraction, fraction again, 33399 over 162. And that's 4.5. I don't need to do 904 there, 902. So this is 28.7 degrees. All right, I'm just going to call it that and move on because time is ticking again. Number 5, the fixed point X and Y lie on the horizontal ground. This is projectile. T equals 0, projected from X speed U at angle theta. Particle P moves freely under gravity and first hits the ground at Y. Show that xy equals that. So this is basically just using algebra. So we can do, well, there's a lot of things we can do here. If we want to find xy, we can find time first. So we can use v equals u plus at, knowing that a is minus g, right? So v and u will be the same value, right? So v here, this is talking about the vertical direction, guys. Okay, this is the vertical component. We can use a Suvat equation. But v here needs to be resolved, yeah? So v there would be the initial speed times sine theta, right? Yeah? Sorry, that would be the u. I meant u, yeah? So this is u sine theta. A is a minus g, t is a t. Now, what about v? Well, because if you look at this image here, which is probably the same as the case in question A, because it hits the ground, it starts from the ground. So when it hits the ground, the vertical component will have the same magnitude, but it's just opposite direction. So instead of u sine theta, we're going to have minus u sine theta when it hits the ground, downwards. Right? So if you rearrange, make gt the subject, you get 2u sine theta there on the other side. And that means t would be equal to 2u sine theta over g. So this is just the time. Now, because we know that the horizontal has the speed as a constant value, and that is u cos theta. If we multiply with time, which is the one we just found, that is going to be xy, right? So there you have, so u squared and then 2 sine theta cos theta over g. And using double angle in P3, you can see that it is u squared sine 2 theta over g as required. So that's part A done. Part B, right? This is long. Okay. The point lies horizontal ground AC. The pole AC, a vertical pole CD, sorry, 5 meters. And the end C is fixed. The ground between A and B, like that. AC is 12 meters. At time t, particle Q is projected from A with the speed 20 at an angle that to the ground. Particle P moves freely under gravity, passes over the pole at first, hits the ground at B. Okay. Find distance CB. Well, isn't that just plugging into the formula we just found? Okay, so, okay, yeah. So we can find AB first using that formula. U is 20, 20 squared, sine 2 of 60, right? Yeah, 2 theta. And then all divided by G, which is 9.8. Okay, we can find that easily, which is fine. But then CB would be AB minus 12. So we can just use a calculator here. Our best friend, 400 times sine of 120. And then divided by 9.8. That would be totally AB. And if you do minus 12 there, you're going to get 23.3. I'm just going to do 3, 4, 7, 9, blah, blah, blah. And I'm going to round that up to 3 significant figures. Okay. Or maybe 2, right? Because normally I should change all the questions to sig figs. Okay, find the height of Q above D at the instance when Q passes over the pole. So it's just that point there. That means the horizontal component here of displacement would have been 12 meters from the start. So we want the point where the time passes by so that it is at C, okay? Okay, so at C, time will have passed by what value? We're going to find that. So time is equal to distance over speed. And the speed component, sorry, the velocity component, the horizontal component of velocity would be 20 cos 60 degrees, right? That will be the time that has passed at C. Now, cos 60 degree happens to be 1 over 2. So 1 over 2 times 20 is 10. So that is 1.2 seconds easily. Okay. Now, we can use this time to find the vertical component. All right. So vertical component is, we want the height, right? So let's use Sy equals Uyt plus 1 over 2 At squared. Yeah. Okay, so that will be the height above C. So U is what? U is 20 times sine of 60 degrees times 1.2, the value we just got. Acceleration is taken as a minus because we are moving up, but gravity is acting down, and that is 1.2 squared. So here's going to be distance, yeah, the height, yeah. So let's do calculator times sine of a 60 times 1.2 plus 0.5 times, let's do a minus here because we have a negative term there, times 1.2 squared. So I have 13.7286, blah, blah, blah. We want the height of Q above D, not the height above the ground. So height above point D is equal to the total height minus 5. Okay, so that's going to be in my calculator minus another 5, I think. Yeah. So that's 8.7 meters. That's done. Let's skip to the next one. I think we're still good with time, I hope. Okay, so number 6. A uniform beam AB of weight that, so this is static equilibrium, I guess. Rests with an A on the rough horizontal ground, a package of weight, blah, 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 blah. So show that K is 56 over 13. What is K? K is the magnitude. Normal reaction between the beam and the peg at C has magnitude KW. So they do everything in W in this case, because the weight is also 5W. Okay. All right. So the normal reaction between the beam and the peg. Okay. So let me draw that quickly. So this is the peg here, and that is the normal reaction. Yeah. This is what we want. Is it? There's a black dot there. Black dot there is a package of weight W. Okay. Okay. This is a package weight W. This is 3A, this is 9A, this is angle theta, this is NA, C, and B. All right. So, okay. Yeah, the uniform beam has a weight 5W, so 5W must act around here where it should be 6A from A. Yeah, because it's uniform, so the center of mass is at the center. Okay, we have rough horizontal ground, so that's going to be friction, but we're going to take moment, guys. Moment at A, yeah? So we don't need to consider the friction at A yet. Okay, so taking moments at A. So we have the moment from the weight, 5W, being clockwise direction here. So I'm going to just resolve the distance down the perpendicular with the force. Some people might prefer resolving force to perpendicular to the distance, but I'm doing distance here. So I'm doing 9A resolving down. Down is close. We use cos here. So that's cos theta. Okay. Yeah. If you want to see the tactic I use to resolve distance, you can check out the link in the description. It's just my TikTok channel, actually. Okay, yeah, so that's the moment clockwise. And we have another clockwise moment from the package on top there. So that's W. Again, this is 12A. Wait, hang on. That's not 9A, that's 6A. Sorry. Almost flopped there. And W here should be a 12A cos theta as well. That's going to be put equal to, I'm out of space there. The clockwise anti-clockwise moment. Actually, I still do have space. R, but this is 9A, right? So 9A is from, yeah, AC. So this is 9A. And now A will cancel. Wait, hang on. That should be an A here. A should cancel. So R will be in terms of W. And because tan theta is given to be 5 over 12. So doing trigonometry there, or Pythagoras, sorry, actually, we get a 13 here. So that is an easy technique that we can use to just quickly find the cos, because we don't want to find the angle directly. I mean, we could, but we don't need to. We can get the cos by doing that trick, yeah? So I have 5W times cos theta, which is 12 over 13, looking from that triangle, plus W, another cos theta here, equals 9R, all right? So wrapping up all the terms, so I'm going to have over 13 here, and this is 60W plus 12W, so that's 72W, and 9 here, moving from R, so this is going to be equal to my R in terms of W. Yeah, 9 can cancel with that, get 8, so I'm getting 8W over 13, but that's not what we, has a magnitude. Huh. Okay, that's weird now. It's not what we expect it to be. So let me double check everything. 5W in the middle. Oh, I forgot 6 here. How can I? Almost. Okay, let's do that again. So R here being, yeah, is given to be KW there. So now we can cancel the W, right, as well. And then doing the math there, just the remaining parts. We have, okay, I'm going to do the fraction there. 5, that's 5 times 6 times 12 plus the top part of the fraction there. So that's 372 divided by 13 and 9 move down here. I'm going to get K. Hopefully that should be divisible. No. Oh no, it's not divisible, guys. I'm in trouble. I'm in trouble. 12, 13. Well, I forgot 12 here. Ah, I forgot another 12 here too. Oh man. Okay, so this is not that now. It is instead 5 times 6 times 12 plus 12 times 12, right? So that's the top bit. That's 504. Let's divide that by 9. Yes. Let's do, hey, hang on. 504 divided by 9. Yeah, okay. 56/13 as required. Okay, so B. The coefficient of friction between A and the ground is mu, given that the beam is resting in limiting equilibrium. So that means it is about to slip. All right, or tilt. Yeah. So in the common sense, I think it should tilt rather than slip, because you have a mass on top of B there. I mean, if you use a common sense, it should be about to tilt towards B, right? Okay, so that means if we redraw the thing again, friction. So imagine if it's tilting this way, it's gonna move the base here this way, right? Yeah, that means friction is gonna be this way. So this must be the friction. Okay, so get the sense of the friction, right? Because it can be either way, actually, depending on the case. Okay, so if friction is that way, we need to find the coefficient. So we need to find this reaction as well. Let's put it as N because we already have an R here. Well, so that is, yeah. Okay, so again, this is 5. What is it again? The weight, the package is W, not 5W. And then the mass here at the center, the weight, 5W here. Okay. Yeah, I think we can use the answer from the previous part as the reaction, I think. So, but do we need it? Yeah, it's still the same, right? So this is 556/13 W. Yeah. Okay, we can use force here, forces, right? So is that all the forces we have? Yeah, seems like that. Okay, but what is this angle right here? Because we need to resolve only this vector. So because this is theta, that is going to be theta. So that must be 90 minus theta. And that means this is going to be theta. Okay, quickly there. All right. So doing the force in 2 axes, X first. So friction is mu N. Yeah, so mu, we want to find the mu N. Yeah. Equals, well, the leftward force seems to be only one here, 56W/13. So this is the far away side. Again, the trick is the sine theta. Okay, further away. And that is what? Sine theta is 5/13. Yeah. So yeah, we get the N for this, right? Okay, we're going to solve simultaneously, but let's wait for that. We're going to keep it as that first, right? You don't need to simplify yet because if you don't have any plan, just keep it like that. All right, that'd be my recommendation. Now, again, for the y, right, we have n plus 56 over 13w. Now this time cos theta, which is 12 over 13, equals the downward forces, w and 5w. I'm just going to write just for the working there. Okay, that's it. So it seems like we can now make n in terms of w. So I'm going to move everything to the right side. We're going to have 6 on the right side minus. So that's going to be 56 times 12. I get 672 over 13. And then brackets w. So that is what? That's a minus. Hang on. That's not possible. Does this mean friction is overcoming that? Yeah, maybe my assumption is wrong now. So if friction is the other way, no, that's not possible because you have reaction here. Yeah, you have reaction. Yeah, that should be. Yeah, friction should go that way, guys. But okay, n plus that equals 5w plus w. I don't know why this is getting. Okay, so okay. Normal reaction between the beam and the pick is quite great. Yeah, it's just that when you subtract that, you get a minus number, a negative number, which is not quite possible to me. Wait, hang on. 56 times 12 divided by 13 times 13. Ah, that's what I missed. Sorry. Because I forgot one of the 13. This is what's wrong when you do mental math. Yeah, okay. So, all right. So where was I? I got to do that. So 6 minus that, right? So n is, okay. No exact value needed. So let's do that. So mu is going to be F over N. Sorry, from the first equation, mu is already this one. Mu is already. Wait. Oh, this should be in terms of W. Right. So mu would be, okay, so 56 times 5 over 13 squared W divided by N, which is that W. So W get cancelled. I'm going to follow through this answer and doing 56 times 5 divided by 13 times 13 and then times the answer. Math error? What? Okay, you know what? I'm going to just do everything again. So this is 56 times 5 over 169W. And this will be what? 6 minus 56 times 12 divided by 169W. So mu will be 56 times 5 over 169W divided by the n, yeah, which is that guy. So I'm going to have to put this into my calculator now to get maybe hopefully exact. I don't know. Because I don't see any simplification there. So 6 minus fraction 56 times 12 over 196. Yeah, okay, yeah. 0.82 maybe. Let's check everything if I put everything correctly there. Um, yeah, I'm happy with that. So we're just gonna move on now. We are time is ticking. I hope this is the last question. Am I wrong? Am I right? Yes, I'm right. Okay. Particle P has a mass 5m and particle Q has a mass. Okay, this is about collision and momentum. No, it's a coefficient of restitution. Yeah, kind of momentum, right? Okay. Find the set of value of E for which the direction of motion of P is unchanged as a result of the collision. Okay. So the E here, basically the principle of E is the speed of separation, because that's where what happens after the collision, and divided by the speed of, this is off here, approach. Okay. Actually, there should be a word relative in front of both terms, but yeah, there you go. So particle P, say that is particle P here, and moving in opposite direction. Okay, so P 5m, and then Q 2m, smaller. Okay, P collides directly with Q immediately before collision. Speed of P is 2u, and speed of Q is 3u there. Okay, immediately after the collision. So let's do that as before. So this is after the collision. Speed of P is x, and the speed of Q is y. The direction of motion of Q is reversed. So Q should go that way with the speed of y, but we don't know what Q is, right? Okay, yeah. Now, let's do an E here. E is speed of separation. Let's do the speed of approach first. Speed of approach would be, because if we take to the right as a positive convention, so yeah, okay, it doesn't have to be that way, but anyway. So speed of approach would be, if they head-on collide like this, it's going to be adding them up, adding the speed up. So that's going to be 5u. So 2u plus 3u, right? And the speed of separation, right? So let's put that as an x first. So, and then separation, right? So if we assume that x goes that way, yeah? So the speed of separation would be y minus x, right? Yeah? But if x goes the other way, so if x turns to be a negative value, this is going to be y plus x, but we are taking x as a positive. We've taken x as a positive value. So that's it. Now we want the set of values of E for which the direction of motion of P is unchanged. So that means x must be a positive value, right? Okay, but here we know that y must be greater than x. Otherwise, it wouldn't make sense. Okay. Okay, let me take a look at more details here. So the values of E. So E must be a value greater than 0 anyway. Yeah. But so if P is unchanged, X must be greater than 0 as well. Okay. And okay, so if X greater than 0 and Y greater than X, so Y minus X would be greater than 0, right? Okay. Um, yeah, I think we're gonna have to set the values. Yeah, that should be inequality, guys. Okay. Yeah, probably we need to do conservation of momentum. Okay, let's do conservation of momentum first. So total momentum before is equal to total momentum after collision. So this is 5m times 2u minus, yeah, taking positive as to the right again, equals, this is 5m times x to the right, also to the right, 2m times y, right? So the m all cancel there, okay? And we have 10u minus 6u equals 5x plus 2y. So 5x plus 2y equals 4u. Okay. Now, if we make y, if we isolate y, we get 4u minus 5x. All right. Okay, so y would be equal to 4u. Yeah, 4u minus 5x. So I'm just going to divide into both terms. So 2u here minus 5 over 2x. Why am I doing this? Because I want to substitute y here because we know for sure that x should be greater than 0. So now E should be putting y in terms of u and x here, minus x divided by, down there is just 5u, right? Okay, so simplifying a little bit more, this is minus 2 over 2, so 2u minus 7 over 2x here, and over 5u. Okay, so this is, if you cancel there, should I do that? Okay, so we're going to start from x greater than 0. So 7 over 2x minus 7 to x less than 0. If we add the 2u, so we have 2u minus 7 over 2x less than 2u, right? And then if we divide that by 5u, then that's going to be less than 2u over 5u. So that is less than 2 over 5. Yeah, so E is less than 2 over 5, but greater than 0. That would be my answer there to A. B, in the collision, Q receives an impulse. Okay, so Q receives an impulse. So impulse on Q would be equal to the change of momentum of Q. And impulse is already given to be 60 over 7 mu. So look, because Q was initially to the left, and after collision, it is to the right. That means impulse should be directed to the right side so that it can go to the right after the collision. So we're going to make an impulse a positive term here, right? And because directions are very important in mechanics here. Okay, so let's do momentum. Hang on. Mass of Q is 2m. So again, change in momentum is mass times the change in velocity. So velocity before collision, sorry, I need to move up and down a bit. After collision is y, right? But before collision is to the left, which is minus 3u. Okay, so that's it. And we need to solve. Okay, here we're going to find the value of y in terms of u, and we're going to put it back to somewhere to solve for u. So this is what? This is 2y plus 6u. If you simplify that, we get y equals, so 6 move to the left here, we get 42. Subtracting from 60, that is 18. Wait, hang on, is it? Yeah, 18. So 18 over 7 times 2 down here because we have a 2y there as well. So that's 9 over 7 u. Yeah. Just checking. Yeah, it is. So we know that already, and we can plug that into one of the equations here to find x maybe. Or we can already, hang on, can we already find u? Yeah. Wait. Yeah, we should use this one. All right. So y, or we can use 2y there. Yeah. Y equals 2u minus 5 over 2x. So we're going to get x. So x will be 2u minus y, which is 9 over 7u, divided by 5 over 2. Just rearranging and making x the subject. All right. So I'm going to get in terms of u, but this is 14 minus 9 is 5. 5 over 7 times 2 over 5. Cancel, cancel. So that's 2 over 7u. Okay, so E is going to be equal to all that. Yeah. 2u minus 7 over 2x, which is that guy. Yep. Over 5u. Hopefully I'm right for this one. Oh no, that is 0. It's impossible. Oh no, it's not 0. This is 1. Sorry. This is 1 over 5. Yes. Okay. 7 minutes. 7 minutes. After the collision Q hits the smooth fixed vertical wall that is perpendicular to the direction of motion Q. Okay, so Q is going to hit this guy. Particle Q rebounds. There is a second collision between P. Okay, so P is still moving. Coefficient of restitution between Q and the wall is 1/3. Okay, so after Q is hit by P in the first collision, the speed is y. Okay, so speed is y before collision because y here is equal to, what's the y again? 9 over 7u, right? So after collision here, yeah, rebound would be u of q here after rebound equals, well, approaching a wall and separating from a wall because the wall doesn't move at all. So you can use E to multiply this initial speed to get the final speed already. So that's going to be 1/3 of the wall, right? So that is 3 over 7u. Yeah. So that is the initial speed of Q when it's going to hit P again at the second collision. Okay. Impulse received by Q in the second collision. Ooh, all right. Change in momentum. Okay, so we gotta do conservation of momentum again. Conservation of momentum. Okay, so P is gonna move by the X, where X is what? X 2 over 7u. Okay, so let's do 2 over 7u times, what's the mass of the P? 5m, yeah? Minus, because Q is moving to the left, and mass of Q is 2m. And the speed to the left is 3 over 7 after hitting the wall. Okay. And then that's tricky. So, okay. Let's say that Q is going to be to the right, yeah? And P is going to be to the right. So let's assume that they both to the right. Okay, so after collision is like that again. Okay, so that's going to be equal to 5m. This is, say, Vp plus 2m Vq. All right, so that's after collision. So canceling m. So we get 10 over 7u minus 6 over 7u here. So I get 10 minus 6. I get 4 over 7u. My time is running out. This is 5vp plus 2vq. Okay, so coefficient of restitution is 1 over 5. Speed of approach would be, sorry, speed of separation on top. So I'm assuming Q is ahead of P after collision. So we do VQ minus VP divided by the speed of approach, which is 9 over 7 minus 2 over 7u. So that's 7 over 7. That's u. No, hang on. We should add them up. So that's 11 over 7u. All right. Okay, yeah. So that's going to be VQ minus VP equals 11 over 35U. Okay, so I'm gonna multiply that by 2. And then I'm gonna add up the equation here. So I get adding them up. I get this one, adding this one, I get, no, not adding them up, subtracting them. Okay, so subtracting them would give me 5VP minus VP, so that would be 6VP on the left. And then this one, subtracting this one, right? I get 4 over 7 minus 22 over 33U. Okay, so this is, oh no. Okay, 20 minus 22. I get a negative U. That's not possible. Oh, it might be. Okay, so VU is, so this is, so VP, sorry, it's, that's 1 over 6 cancel with 2. I get, this is a minus. Okay, I get 3 times 35. I get 105. So that's minus 105U. So that is implying that P is actually moving to the left. No, yeah, to the left. Right. So impulse received by Q will be equal to the impulse received by P. So received by P is 5M. Final is to the left, so that's that minus to the right, which is 2 over 7U. So that's going to be 5. Okay, I'm out of luck here. 3130. 150 over 105 MU. So this is 30 over 21 MU, or 10 over 7 MU. Sorry, yeah, I'm done. All right, guys, here's the mark scheme, October 2024 M2. The last question got me. All right, but I have no idea how well I did, but because I didn't have time to double check at all. So let's take the first one here. Yeah, I think I got the time right, 6 over 7 there, just happened to see that, but what's the first one here? Yeah. So RVD, okay, yeah, that's right. And the second one here, integrating. Yeah, okay, yeah, okay. Yeah, I got it. There you go, 8745. 1B, A is dV by dt, and then blah, 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 acceleration 50. And then the time there, 6 over 7. Yeah. Number 2. Okay, impulse. This one took away quite some of my time because I made a silly mistake here. Didn't multiply 3 into the brackets there. But I got it right here for this one. 3, 7, 8, and then 9 and 6. Yeah, got it. Number 3. Yeah, this is about energy. So 0.6. Yeah, that's right. Good. 3B, use work energy conservation. Still got it right. Number 4 is about center of mass. Yeah, I didn't do table, but anyway, yeah, you can do table, of course. Might be a good idea, but I got it right there. Yeah, because I could prove. And this one, ooh, this one is horrible. I didn't get it. Yeah, that should be, so this should be 225 over 2 minus 261 over 6, I think. And then doing the fraction there would give 828 over 12 times 27. Yeah, so this is 23 over 9. So I just did a wrong mental math there, basically. I mean, somehow, not a mental math even, I did something wrong with the calculator. All right, so how many marks did I get for this? I think yeah, this is just to prove that this method works, guys. It's just if you use a calculator properly with a proper calculator, that should be fine. Yeah, so that would have been the y value that should have been right. So expression for relevant angle. So I think I lost one here. Okay, and because I follow through there, I just lost another one here. So 2 marks. That hurts. Number 5. Yeah, so this should be right. Yeah, cool. B 23 meters. Yeah, 23 is fine. C 8.7. Yeah, cool. 6, all of that. And then, yeah, that's also right. That's it, number 6. Okay, okay. That's easy. Number 7. Yeah, this one. This one. Yes. Yeah, good. Well done, base, for that. The impulse momentum equation, of course, I did that. And I proved that to be 1/5. I managed to do that. Wait, did I get that right? No, no way. No way I got that right? That was just last minutes. Okay, but anyway, how many marks did I get? I get 3/7 there for the speed of Q. That's B1. And then the magnitude of impulse. What? I mean, I don't seem to find any trace. Oh no. I used the wrong value. I used this. So when I add these up, I got 11/7u, which should have been 3 plus 3u/7 plus 2u/7. So that should have given me the exact same thing as the mark scheme says here. And if we use that, work on this, we should get the final mark. And that should have made sense. That would have made sense. But yeah, I think I got the method marks here, guys. Yeah, because I tried to do that, but didn't manage to get the final accuracy there. So I'm just going to say here, this is 1 minus 1. So I lost -1, just 3 marks, I guess. That's what I saw. 3 marks. Yeah, 3 marks. All right, so this paper is 72 out of 75. Yes. So in my opinion, question 1 here is kind of okay. You just got to be thorough, right, in doing the calculus on the vectors there. But maybe you might find my technique useful when you deal with the initial conditions where you need to substitute. So you can cut out a lot of algebraic work if you just do that technique. So you can go back to see the first question, how I do that. The second question was okay, but you got to be careful with the components in the vectors, and when you do the algebra separately in the y and the I and the j components, right? Yeah, this is basically impulse with energy. If you're not careful, again, the textiness of the question might get you carried away. And if you're not focused on getting straight to the point, yeah. So basically, when you see connected particles, you always think of Newton's second law, right? And connected particles, acceleration the same, velocity the same, right? That would be my recommendation. This one, yeah, this one is fine. I made a mistake on this, a silly mistake. Yeah, couldn't avoid that. Yeah, you just split the shape into more parts and then do the center of mass calculation. This one, yeah, use subtraction method. And I would find the new center of mass and just draw the line, the vertical line. You can go back and take a look at how I did it as well. So, but that was all fine, except that I didn't manage to get the accuracy mark there. So I lost 1 mark there as well. And yeah, this one was all fine. Projectile. So try to revise on how to prove the algebraic formula in projectile motion as well. Okay, like for example, A, and there are a couple of more. You should check the textbook because this is the most recent year as of the time of recording, and it came up, right? I mean, you saw this in the book. This is even in M1, guys. And the second one here is quite easy. This is an easy projectile question, but I think most candidates will make a mistake on this because they thought that they would find the height at C, but it's actually finding the height above point D. So they might lose 1 mark there, most people. Okay, or maybe not. Now this one, but yeah, you got to be careful with a lot of algebra there. Usually, this kind of question, static equilibrium, will start with moment first. If you notice, right, it is usually starting with moments. So moment is like the usually the first thing you take in order to solve like the first question in this static equilibrium. And the other thing you got to be careful is friction. You got to make some sense out of friction first. Otherwise, you're going to get a negative value in some part, and that's going to slow you down a lot. This one was a real deal. So yeah, it's just that I used the wrong speed in my messy diagram. So that was a silly mistake to me, I think. I used the wrong speed. So I would have got that if I didn't make that mistake. But coefficient of restitution is the key here. So it is speed of separation divided by the relative speed of approach. And always be careful about the direction. So I hope that was all useful. Please hit subscribe. That would support us by a lot. And I hope you guys keep studying. Good luck.